in this picture. So the bioactivity which I am going to explain, so I'll be taking the example of respiratory system, how we can understand the bioactivity in terms of nanometallic pollutions and how we can prevent that. So these are the few things we will try to understand. This one you have already seen, so this interface is very, very important. This is lined with the surface active molecules between the lung air phase, that is the air spaces, in alveoli, and then the fluid phase. And this is the one that is disrupted bilayer of the interfacial surface active molecules. So it could happen because of any reason. But the main purpose here we will be talking about that what causes it. Today we are going to talk about that. So that is the suspended nanoparticles in the form of bioactive ingredients which have the ability to instantaneously interact with such kind of bilayers. Last time we were told that the pulmonary surfactants which help us in the breathing processes, so they are mainly made up of lipid molecules, DPPC 70% and POPG 30%. So these are the molecular structure. You could see that they are the zwitterionic. This one is particularly the zwitterionic molecule with double hydrocarbon chain, and in this case POPG is the sodium salt, and it is the anionic molecule because there is a negative charge on the phosphate, and there is one unsaturation in the hydrocarbon chain. So the combination of all these lipid molecules, they create the bilayer assembly that is absorbed at the air alveolus aqueous interface. Apart from that, there are surfactant proteins. So there are 4. 2 are hydrophilic, 2 are hydrophobic. If you are the student of biology or at some point you have studied biology, you know what is the meaning of a protein. So proteins vary from one another because of the sequence of the amino acid. So all proteins are predominantly made up of amino acids. Only the sequence of the amino acids, so they are going to configure the properties of the protein. Some of the proteins are water soluble, some of the proteins are water insoluble. When the number of amino acids which are water soluble, they exceeds that exceeds the number of water insoluble or predominantly non-polar amino acids. So then the protein is water soluble, otherwise it is water insoluble. So water soluble proteins are known as hydrophilic proteins. The water insoluble or sparingly soluble are predominantly hydrophobic proteins. Protein, it is not excluding the possibility of hydrophobic domains in the case of hydrophilic, and situation for excluding the possibility of hydrophilic domains. Schematically, I can say that this is a protein molecule. Okay, so you may have somewhere over here predominantly hydrophilic and hydrophobic. If I say this is hydrophilic domain and this one is hydrophobic, or sometime the hydrophobic domains are hidden inside the protein aggregate structure by the hydrophilic domains. So when the protein unfolds, something it is like this, and sometimes you will see that the hydrophobic domain, if this is the hydrophobic domain, it comes in the vicinity of aqueous phase. So this is known as protein folding. There's a native structure of the protein. Native structure exists at a particular temperature and the pH. And when we alter the environmental conditions, we can unfold the protein. So that is the meaning of the hydrophilic and the hydrophobic. What we have done in our lab, we create the artificial lung in the apparatus. Now, it is not exactly the way we have the lung in the human body. It is a kind of apparatus where the functioning of the apparatus depicts the functioning of the lung. In the lung, you have so many alveoli. So here we have just picked a bubble and we depict this is a one alveolus. Now this is one alveolus. It is exactly at the interface of air and water. Now the surface lining of this air bubble, that is lined with the same composition of the pulmonary surfactants which exist in the human lung. So the same composition, the composition of DPPC 70% POPG, we mix these components along with the surfactant proteins and we inject it into the bubble. When we inject it into the bubble, obviously they created the bilayer the way it is there over here, this bilayer. Now, we know that when we compress the lung, the surface activity should go, which the human body is exerting on the lung. We perform the same kind of experiment by adding the pressure over this. That squeeze the bubble and simultaneously we measure the surface tension. Measuring the surface tension. Initially when we have not applied any pressure, or you can say that we have already air in the lung and the lung is filled with the air and then we are applying the pressure to expel the air. So the amount of, and when we apply that, we could measure the surface tension exactly in the same way as is happening in the human lung. So the surface tension reduces to close to 0 value. You see, it is initially slightly above than the 30 millinewton per meter. And when we compress it up to over here, and you could see that the surface tension reduces to a minimum value. It means that the surface tension of the bubble, when it reduces to minimum value, the bubble compresses. The bubble compresses and whatsoever is there is completely expelled out. Right? So, the rate with which the human lung expands and compresses, the same rate we applied and we try to measure the reproducibility of the surface activity. So you could see that the red plot, the color, the points in the red color, they are representing the compression when we put the pressure on the lung, and the blue, so they represent the expansion. And this clearly shows that the communication which is created by the amphiphilic molecules along with the surfactant protein in the human lung, the way that is working under the natural circumstances in the case of every human being, same composition is working exactly under the experimental kind. Zero, practically there is no surface tension. If there is no surface tension, the bubble will not be like this, but it will be more compressed. Means this is somewhat close to the compression, but otherwise otherwise the bubble will be more expanded under the normal circumstances. What is the meaning of this? The meaning of this is that for the healthy lung, for a normal person, so you have something like this that is being performed by every alveolus. You have thousands and thousands of alveolus in the lung. So here this is just one. So it means that every alveolus in the human lung, so that is performing exactly the same kind of expansion and compression what you could see in this experiment. And the value for the surface activity or the surface tension when the air is expelled, exactly that is close to zero under the natural circumstances, and under experimental circumstances, exactly that is also close to the natural value. It means the composition which we are predicting, which we have 70%, 30%, and it is close to 2% usually, the surfactant protein. It means that in the human lung, almost close to exactly this composition exists. Now, this is the story for the normal circumstances when there is no pollution. We are going to consider the pollution in the form of nanoparticles. You could imagine what if we have pollutants here, dust particle in the form of nanoparticle, and if you are going to inhale them, what is going to happen? So, a pollution model, synthesis of gold nanoparticle capped with pulmonary surfactant as pollutants. In vitro use of gold nanoparticles as pollutant to study their effect on the breathing process. What we did, in order to estimate the effect of the pollutant on the respiratory system, rather than picking the dust particle from the air as the sample, what we did, we picked the gold nanoparticle. The reason was that we synthesized the gold nanoparticle of same shape and size, and then we use them over here to just know that if I'm going to inject the gold nanoparticle into the alveolus, it is exactly the same way as if you are breathing the nanoparticle and they are going into your lung and they are residing in the alveoli. So then what will happen? What we did, we synthesized the gold nanoparticle the way I have already told you, and the stabilization of the gold nanoparticle I have already told you that how we can provide the bilayer. And here the bilayer for the gold nanoparticle is provided with the phospholipid molecules, exactly those which I showed you. And we also saw the bilayer in the transmission electron microscope. So what we did actually, what is the meaning of this? We initially prepared the gold nanoparticle without the presence of the lipid, exactly those lipid molecules which we have in our lung at the same composition. And in that solution, we added our gold nanoparticle which was synthesized the way you did yesterday in the lab. We purified them, we just added them in combination of the pulmonary surfactant suspension. And then we tried to disperse them, and we saw after the mixing, and we get the TAN image, and we saw that the pulmonary surfactant, they created the bilayer around each gold nanoparticle. The most strange results were when we added the surfactant protein, SPB. This represents the surfactant protein which I am mentioning over here. SPA, SPB, SPC, and SPB. We pick the SPB, it is much more surface active. When we added SPB, the gold nanoparticle, which were less segregated in the presence of lipid molecules of the same composition as of human lung, as we added tiny amount of the surfactant protein, the aggregation was enhanced. You see the aggregation? there was less aggregation over here, but as soon as we added tiny amount of the surfactant protein suspension, and then we got the image, and we saw that the aggregation of the gold nanoparticle is now much more enhanced than what is over there. What is the meaning of this? I'm just telling you now. I'll explain what is the meaning of this. It means that the lung surfactants which we have in the human body, they have very high affinity for a nanoparticle. Nanoparticle could be from the gold, could be from the silver, or that could be a dust nanoparticle. They all have very high affinity for the polymerase surfactant complexation. As soon as the particle comes in contact with the bilayer in the human lung, that bilayer instantaneously coats that nanoparticle. No matter that nanoparticle is made up of which kind of substance, whether it could be a transition metal or any kind of oxide like silicon oxide minerals of dust. How do we know this? How do we know that this is exactly happening when you inhale the pollutant particles in your lung? I'm now taking you to that part. So you see that this was the one image, and this is the next one, where before adding SPP you have an image like this, but as soon as you added SPP, surfactant protein B, you see a very intense aggregation. You see the gold nanoparticle? Read the scale bar. The gold nanoparticle is less than 10 nanometer and very clear spherical gold nanoparticle, right? Okay. Now, as I told you that in order to become a good scientist, you have to look for a technique which can be easily applied for your easy detection or the step in which you have to go ahead. I mean to say that suppose if you want to see that there is an aggregation here or there is aggregation here, then what is the easiest technique? The transmission electron microscopy which I am showing over here, probably it is not available everywhere and it's not that easy to instantaneously get the image or the sample. But what is much easier to perform? That is the UV visible spectroscopy. So everywhere you have the visible spectroscopy. What you could do, you could take the gold nanoparticle, the solid red line with POPG, gold nanoparticle coated with POPG, making the bilayer. Then the gold nanoparticle coated with DMPG. I have already explained the nomenclature for these molecules in the previous slides. So when we take these samples without the surfactant protein, you see the sharp band here. That is because of the surface plasma resonance of the gold nanoparticle or the absorbance which you measured yesterday. You prepared the gold nanoparticle suspension and you took the absorbance, and there was a peak close to 500 nanometer. That is the one over here you see close to 520 nanometer. In the same sample, when we added a tiny amount of surfactant protein B, the same kind of suspension of the surfactant protein B, this peak instantaneously shifts to at a higher wavelength with much broader peak. The intensity is much higher over here in comparison to this. So, greater the intensity, greater is the number of nanoparticles. What is the meaning of the shifting towards the higher wavelength? Whenever you have the aggregation in the nanoparticle from here to here, any aggregation which happens in the gold nanoparticle suspension, it instantaneously shifts the gold nanoparticle absorbance to the higher wavelength. So that's what's happening. Apart from that, that peak must be much broader in comparison to the peak that was without the aggregation. So this is without the aggregation, or the tiny amount of the aggregation of the gold nanoparticle. This clearly shows that there is an intense aggregation of the gold nanoparticle. How it happened? This is the first evidence. This is the simplest way of determining that what is happening in the solution. Thereafter, you can perform the microscopic imaging studies slowly, but at least you know that by adding surfactant protein, aggregation is taking place. Now, another important thing, the color of the gold nanoparticle suspension, if the absorbance is close to 540 nanometer, it should be ruby red color. But you are not expecting the ruby red color close to 700 nanometer. It's the visible region, right? So in the visible region, as you are moving towards the towards the higher wavelength, the color changes from ruby red to purple and some other kind of shaded between ruby red and the purple. Now, it shows that the aggregation has happened. You can perform another very simple experiment, that is the gel electrophoresis. It is everywhere in the biology lab. What you could do, the same sample without the surfactant protein B, if you are going to put it in the gel well here for POPG, apply the voltage, you see there is a transfer of the electrons, the transfer of the nanoparticles towards the positively charged electrons, because these POPG are predominantly negatively charged. So hence the shell that is being created, the bilayer shell that is being created on the surface of the nanoparticle, that is predominantly negatively charged. So it means that they are going to move towards the positively charged electron. But as soon as in the same sample, if you are going to add the surfactant protein B, now the aggregates are very large enough, they cannot move through the channel of the gel. So hence there is no shifting of the aggregated gold nanoparticle in the presence of surfactant protein B and surfactant protein B over here. This is another evidence that intense aggregation has taken place. But you will be wondering, how is it related to respiration? I'm coming to that point. What is happening schematically? This is one gold nanoparticle, this is another gold nanoparticle, this is another one. This is the bilayer of the polymerase surfactant. BMPG or POPG, you can say bilayer of the phospholipid molecule. Exactly those molecules which are there in the lung. Now, initially they are separated from one another. They have the colloidal stabilization in the solution. Fine regular suspension, colloidal suspension. But as soon as I'm going to add the surfactant protein B, this is the overall schematic representation of surfactant protein B. So it is showing the various domains. You don't need to go through that. When we add this, the surfactant protein B, which I have shown schematically over here, that has the ability to bind with the bilayer of the adjoining nanoparticle. So therefore, it is acting as a glue. It is facilitating the aggregation in this way. Different nanoparticles which were quite separately separated from one another, suspended in the aqueous solution in the absence of surfactant protein B. But as soon as we are going to add surfactant protein B, this kind of association, surfactant protein B with the polymerase surfactant, instantaneously induce the aggregation, and that aggregation shifts the absorbance to the higher wavelength and stops the displacement of the aggregates through the gel network. So now we are coming back to our artificial lung. So this was the normal artificial lung functioning without the pollutants. Now we have created the model pollutants, gold nanoparticle with phospholipid. They act as a model, not exactly the pollutants which you have in the air, but they can work exactly or very closely similar to that of the pollutants. What we did, we picked the sample of the gold nanoparticle. This is the sample, the gold nanoparticle, and we added DPPC, POPG and SPP in the gold nano. We took this suspension actually, and we added the purified gold nanoparticle, and we produce a stable suspension. Now this suspension we injected into your artificial lung or artificial alveolus. This is artificial alveolus. And we performed the same experiment. Same experiment, expecting that after the compression, the surface tension should reduce close to zero as it was happening earlier. See over here. It was coming close to zero in the absence of pollutant. But when we added the gold nanoparticle as pollutant, as model pollutant, so we were expecting that the surface tension after the compression should come in close to zero, but that is not happening. So the surface, you see, initially that could be higher value, but it is the minimum surface tension we are achieving close to only 20. This value should have gone to touch 0 milliNewton per meter, but that is not happening. What is the meaning for this? It means that the compression with the pressure we apply to expel the air or to squeeze the bubble, now that is not working. Why it is not working? Because the bilayer, the interfacial bilayer that is present at the air and the aqueous interface, that is not possessing the sufficient amount of the surface activity that could reduce the surface tension. What is the meaning for this? It means that if the pollutants are going into the human lung, then the functioning of the human lung is impeded exactly the same way as is happening over here in the experimental artificial lung. Okay, so this is a clear evidence. It means that when the pollutants are added, this is the natural surfactant. Without, if I do not add the pollutants, there is no problem. The artificial lung experiment is working exactly the natural lung. But when I add the pollutants, then the artificial lung is not working as a natural lung. So it means that the artificial experiment clearly shows that the pollutants have impeding effect on our respiratory system. Now we will try to look into the microscopic picture of the bilayer in the lung. What is happening? I told you that the bilayer is created by the vesicular system. It is the vesicle. I have shown just part of the vesicle over here. Reminding you once again which were the vesicle we were talking about. These were the vesicles. Lamellar bodies. They were going over here, opening up, producing the bilayer. Right? Over there you can see opening the bilayer. So I'm talking about it. And I'm just taking the part of the sketch to explain microscopically what is happening at the molecular level. So this is air-liquid interface. You see the vesicle that is coming at the interface and then opens up and creates the bilayer. Okay. So in the bilayer, this bilayer is created. It has, I have shown only the monolayer, but because the reason is air is non-polar, so therefore the upper side should be lined with the hydrocarbon tails, hydrophobic tails, rather than the head group. So head groups are inserted only in the lung fluid, that is the aqueous phase at the interface. So that is why you see only the monolayer exactly at the interface. Proposed mechanism for the pollutants absorption at the air alveolar interface. Injured lung means impeding the functioning of the lung. How that is working? Okay, these are the gold nanoparticles. These are the gold nanoparticles. All the pollutants, they are coming from where? They are coming from the air, not from this side. There is no way the nanoparticle travel through the body and enter, and they can come at close to the lung. So what you inhale the air, if that is polluted with the pollutants, so then the nanoparticles are going to hit the layer, interfacial layer of the phospholipid molecules. As soon as they are going to hit it, instantaneously the phospholipid molecules will create a bilayer. This is the bilayer. You have proved this because you have proved this when you are adding the gold nanoparticle in the phospholipid suspension, you are creating a bilayer. So you have already seen in the experiment, and that is what is happening under natural circumstances when you face the pollutant. So now, so what if the pollutants are, because everybody is inhaling dust particle and everybody is very healthy, right? So there is no issue. Yes, absolutely there is no issue. Where they have gone? They are taken up by any kind of foreign particle, living or non-living, that enters into the lung during the respiration, is taken up by macrophages, alveolar macrophages. They are there in the lung fluid. So any foreign particle that enters through the interfacial layer, instantaneously taken up by the macrophages. Suppose if you ask me, so we know that for the soft particle or any kind of living organism that enters into the lung during the respiration, right? So we can understand that these macrophages, they have the ability to kill it and to split it. But the problem is these particles are the metallic particle, crystalline particle. Our human body has no ability to disintegrate the crystal into its component. That is not going to happen. So then, when you inhale the dust particle, now those are the silicon oxide minerals. Where they are going, right? So this, I think the better answer probably, professor of medicine can give you. I don't have that answer, that where they end up eventually, but that is a very, very interesting part in biology. But the thing is, why would the respiratory problems are going to arise because of the pollution? It means that something is happening. Something is happening. Okay, so I have 15 minutes. Sorry. Okay, something is happening. Something is happening with this mechanism. The rate with which the particles are entering into the lung and the rate with which they are being cleared by the alveolar macrophages, if that is going to be disrupted, then the problem arises, right? As long as the rate is the same, there is no issue. Every day you are inhaling dust particle. So much pollution is there. But those people where this clearance from the lung fluid by the alveolar macrophages is going to be disturbed, only then there is a problem. Then, what is the problem then? Then the particles will remain here. The concentration of the particle is high rather than the rate with which they are being cleared from the alveolar macrophages, and hence the particle will start residing over there and will disrupt the continuity of the interfacial surfactant layer which provides the surface activity. The one I have shown over here. In this diagram I show, but this could be because of your other health issue, biological health issue, but if we have to look at the pollutants, it will become a permanent issue because you have a certain concentration of the pollutant. It is always there because you are constantly exposed to the pollutant. And the alveolar macrophages, those are like this. They have not that much ability or capacity to remove all the pollutants. It means that your interfacial phospholipid layer along with the surfactant protein can never be a continuous film, and hence you cannot have the close to zero surface tension during the respiratory expansion or compression. This is the thing which shows over here. Okay, so this continuous film is required in order to perform the healthy respiration. When it is disrupted, so these particles are already there. Macrophages has limited ability to clear them, and now you see it's a non-continuous, so therefore it cannot provide the required amount of surface activity. So now it means that this film is now uncompressed. It cannot be compressed to the value that leads to the surface activity close to 0 millinewton per meter, right? Since this part is not lined with that of the phospholipid molecules like this part, so it's a non-continuous part. So now, on the basis of this, we can conclude that metal nanoparticle as air pollutants have strong interaction with pulmonary surfactant. This is the metal nanoparticle as model. But if you ask me, what if there are dust particle or the carbon suspended fiber or the particle from the fossil emission? They are also having the same kind of affinity. Maybe there could be a slight variation because this is the surface of the transition metal as a gold nanoparticle for the silicon oxide. So they are the silicon oxide mineral particles. Surface properties are not exactly the same as that of the transition metal nanoparticle. And for the carbon particles, they are completely non-polar. Obviously, their surface properties are much different. So in all the cases, but the phospholipid molecules, so they have the dual affinity to interact with the polar as well as the non-polar surfaces. So they have no matter the particle which you are going to inhale, they are polar, they are possessing the charged surfaces or the non-polar surfaces. They are going to be complex with that of the phospholipid molecules because the phospholipid molecules have dual ability to interact with both the charged surfaces as well as the non-charged surfaces. Constant exposure of air pollutants can produce respiratory disorder, and this is the problem which we see normally happening whenever we have a constant range of you lie in your life for the children, adults, or the elderly. So just concluding statement. So we started our lecture by talking about the bulk soluble and the surface active nanomaterials. You see the nanomaterials we have shown in this lecture. There is no doubt they are bulk soluble because they are coated with the phospholipid layer. But when they interact with the surfactant protein, they absorb at the biointerfaces. The lung surface is the biointerface. There is air phase as well as the lung fluid phase, that is the aqueous phase. So therefore, we know the impeding effect of, or the intense toxic effect of the pollutant, how they can interact with the biointerfaces. So this is just one example. This is not the only example how the pollutants are going to interact with the biointerfaces. We have so many biointerfaces In our alimentary canal, we have also biointerfaces. Everywhere on the open wound, we have the biointerfaces. So it means that we have plenty of other examples. Suppose if you want to read more article or more information to gain in this direction, I will say that just look for the publications which talk about the interaction of the pollutant with the bio surfaces, and you will have much more information. Thank you so much.
of oxide particle.
Uh, Predominantly, we will be talking about the same aspect of the iron oxide
Oxide
nanoparticle,
nanoparticle,
which
which
we
we
have
have
learned
learned
for
for
the
the
gold
gold
nanoparticle
nanoparticle
and
and
the
the
synthesis.
synthesis.
Some points which are very unique in this case. So the focus is on that very important point, that is the surface activity. You have seen that we have defined
Defined
or explained the
the
definition
definition
of
of
surface active molecules.
molecules
Those prefer to remain active at the
that the
interface,
is
no
no
matter which interface
it
it is.
is.
So
So
now you will see
see
that
that
how
how
can
can
we
we
produce synthesized
size
surface
surface
active
active
nanoparticles. So there is a difference between, I'll explain in this lecture, that
that
what
what
is
is
the
the
difference
difference
between
between
surface
surface
active
active
molecule.
molecule?
You are
You are
very
very
familiar
familiar
about
about sodium 2 dicyl sulfate, which you added in the gold nanoparticle suspension yesterday to make it a stabilized colloidal suspension. So, sodium sulfate is a surface active molecule, and in I'll explain that how we can produce the surface active nanoparticle. So, if somebody asks you that dimensionally, how big is the nanoparticle in comparison to a molecule?
So the molecule,
Molecule,
the
the
dimensions
dimensions
of the
of the
molecule
molecule
lie
lie
within
within
1
1
to
to
2
2
nanometer
nanometer
range.
range.
It's
It's
very
very
tiny
tiny
size.
size.
Smaller
Smaller
nanoparticle molecules
molecules
are
are
like
like
carbon
carbon dioxide.
dioxide. They are
They are
even
even
less
less
than
than
1
1
nanometer in
nanometer in
size,
size,
most of
most
the
of the
molecules.
molecules.
But the
But the
bigger
big
molecules like surfactant
surfactant
with
with
long
long
hydrocarbon
hydrocarbon
tail.
tail.
So
So
you may
you may
say
say
that
that
their
their dimensions
dimensions are close to 1
are 1
to
to
2
2
nanometer.
nanometer.
So
So
usually
usually
close
close
to
to
1
1
nanometer.
nanometer.
But
But
the
the
nanoparticles,
nanoparticles,
the
the
surface
surface
active iron
iron
oxide
oxide
nanoparticle, which
nanoparticle,
we
which
will
we will
talk
talk
about,
about,
so
so
their
their size
size is
is
close to
close to
25 to
25 to
50
50
nanometer.
nanometer.
Means
It's
actually
actually
25 or 30
30
times
times
bigger than the
the
surface
surface
active
active
molecules.
molecules.
So the
So the
obvious
obvious
question
question
is
is
that
that
if we
we
have
have
the surface
surface
active
active
molecules,
molecules,
we
we
know
know
the
the
properties
properties
of
of
surface
surface
active
active
molecules
molecules
from the
from the
molecular
molecular
structure
structure
of the
of the
molecule.
molecule.
The
The
molecule is
molecule is
possessing the
possessing the
polar
polar
head
head
group and
group
the
and the
non-polar
non-polar
hydrocarbon
hydrocarbon
tail.
tail.
How
How
can we
can we
define
define
those
those
aspects
aspects
in the
in the
surface
surface
active
active
nanoparticle?
nanoparticle?
So
So
this
this
this we
this
are
we
going to see
see
in
in.
this chapter. Okay,
Okay,
so
so
again
again,
some of
some
the
of the
very
very
fundamental
fundamental
basic
basic
concepts.
concepts.
We
We
have a
have a
beaker
beaker
full
full
of
of
water,
water,
and we
and
identify the interface is
interfaces
the
and
aqueous
aqueous
bulb.
bulb.
This
This
is
is
the
the
water interface, exactly the
exactly the
surface of
surface
the
of
water,
water,
and
and
this is
this
the
is
solid liquid interface. So because of the container, and the interior of this liquid interface we call aqueous bulk. What if we add ammonium chloride salt, a very small
small
amount,
amount of,
you may
you may
say
say
1
1
millimolar,
millimolar,
10
10
millimolar,
millimolar,
and as soon as we are going to add
add
this
this
ammonium
ammonium
chloride,
chloride.
it's an
It's an
electrolyte
electrolyte
split
split
into
into
oppositely
oppositely
charged
charged
ions.
ions.
So ammonium ion tetrahedral shape and the chloride ion. For the time being, you just ignore chloride ions because they are the spectator ions. And the ammonium
Ammonium
ion is
ion is
solubilized
solubilized
by
by
the
the
hydration
hydration
layer.
layer.
Because
Because
of
of
the
the
ion
ion
dipole interaction, ammonium ion is an ion. The dipole of the water, negative end
end
of
of
the
the
water
water
dipole
dipole
will be directed towards
towards
the
the
cation,
cation,
and
and
hence you
hence you
have the
have the
ion dipole
dipole.
interaction, and you
You
have a
have the
hydration
hydration
sphere.
sphere.
Those water molecules which travel under the
Under the
dynamic
dynamic
motion
motion,
during
during
the displacement of
displacement
the
of the
cation in
cation
the
in the
aqueous
aqueous
bulk,
bulk,
they
they
will always
always
remain
remain
bound
bound
to the
to the
water
water
molecule,
molecule,
and
and
hence
hence
they
they
are
are
included
included
in the
in the
hydration
hydration
sphere.
sphere.
They are
They are
not
not
going to
going
be,
to be,
they
they
may
may
be
be
exchanged
exchanged
among the
among the
water
water
molecule
molecule
of
of
the
the
bulk,
bulk,
but the
but the
total
total
number of
number of
water
water
molecules,
molecules,
those
those
are
are
present
present
in the
in the
hydration
hydration
sphere,
sphere,
they are
they are
not
not
going
going
to
to
change.
change.
What if we
We
replace one
one
hydrogen
hydrogen,
out of the four
four
tetrahedral
tetrahedral
positions
positions
with
with
the
the
hydrocarbon,
hydrocarbon
functional
functional
hydrocarbon
hydrocarbon chain
chains of
of
C8,
C8,
C10,
C10,
C12,
C12,
C14,
C14,
any
any
number
number
of
of the hydrocarbon chain methylene groups.
Okay. Now
Now
there is
there's
a
a
problem.
problem.
When
When
you
you
add
add
a
a
non-polar functional group, then the non-polar functional group that is in repulsive interaction with that of the water
water
molecule
molecule
because
because
they
they
are
are
polar.
polar.
But the
But the
polar
polar
functional group can easily interact with the water molecule. Now there is a competition between the polar-polar interactions and the polar-non-polar interaction. Those interactions which will predominate the other, they will decide the fate of the molecule. If the polar-polar interactions are greater in magnitude, in comparison to the non-polar interaction, the molecule will stay in the atmosphere. If the non-polar-polar interactions are going to predominate, in comparison to polar-polar interactions, the molecule will be expelled from the atmosphere. So, this property of the dual affinity or the dual functional group with opposite with polar and non-polar polarities provides the amphiphilicity or the amphiphilic property to the molecules. So molecules, such kind of molecules are known as amphiphilic molecules. Amphiphilic molecules like over here, polar and non-polar. Now, quantitatively, or the suppose if you want to just estimate under what circumstances the amphiphilic molecule is going to remain in the bulk or excluded from the bulk or prefer to remain at the interface is given by hydrophilic lipophilic balance HLB scale. You can calculate it theoretically. So there are different methods to calculate that. It's a very common scale. You can see it on the internet. You can easily perform the calculation. You can choose STS and try to see what is the value of HLB for sodium chloride sulfate. The scale runs from 0 to all the way 18. Right? When the HLB value is somewhere over here, higher than 9, close to 9, up to 18, the molecules with HLB number resides within this part of the scale. They are highly hydrophilic, highly water soluble. It means that if they are highly water soluble, it means that the polar-polar interactions are predominant in comparison to non-polar interaction. The molecule will reside in the atmosphere. On the contrary, if the HLB number for the molecule resides lower to that, less than 6, somewhere between 0 to 6, the molecule is much more predominantly non-polar. It means the polar-non-polar interactions are going to predominate, and hence the molecule is going to be expelled, and that's why it is predominantly hydrophobic molecule. Now, what if we have a delicate balance between the polar and non-polar interaction, then the HLB number is somewhere over here, 7, 8, 9. When the HLB number of a molecule is close to 7, 8, 9, then the molecule is going to absorb at the interface. Air water. It prefers to absorb at the interface. So HLB scale is a kind of a scale which helps us to determine
before performing any kind of experiment that whether a molecule would be predominantly non-polar or predominantly polar molecule and what kind of surface activity we are expecting. This is the fundamental information regarding the amphiphilic property of a molecule. We will be using this. So I have explained this definition because we will use this when we talk about the surface activity of the magnetic nanoparticle. Now, when we add this kind of molecule, which is surface active, which has a HLB number within this range, it prefers to absorb at the interface, and we keep on increasing the concentration. Some point is start forming the mice, which I already talked about in the previous lectures. And you can determine the critical muscle formation by
by performing the surface active experiment or the connectivity experiment if the surface active molecule is ion.
Now, these were some of the preliminary or basic fundamental considerations. What if we take a gold nanoparticle, few gold nanoparticles, we drop it in the glass of water,
and we try to understand that what happens then. As I told you that a bare gold nanoparticle, if you simply drop it in the aqueous phase or a glass full of water or a beaker full of water, right? And then, now, what kind of interactions we are expecting? So, gold is a transition metal. There is a free electron cloud on the surface. Does the free electron cloud provide sufficient potential to interact with the dipole of the water? I mean to say,
this cloud proceeds the free electron cloud, mobile electron cloud, and these angled, they are the water molecule, band structure of the water molecule. Is it possible to have the interactions,
electrostatic interactions
among
the free electrons, mobile electrons, and the water molecule? This is not happening. The reason is because if this is happening, then you do not need to add the surfactant to provide the colloidal stability. Then the nanoparticles, they themselves are the colloidal particle and they can produce the stable nanoparticle suspension, but they are not. What will happen if you are simply adding the gold nanoparticle, then van der Waal interaction, matter attracts matter, van der Waal interaction predominate than such kind of interaction. You cannot exclude these interactions, but they are not strong enough to provide the colloidal stability. So then the van der Waal interactions predominate, thereby the nanoparticle which you have added in the aqueous bulk, they will fuse one another and they will settle at the bottom under the effect of gravity. So this is the case
happens without the stabilization. And in order to avoid that,
we add the
surfactant molecule.
Yesterday you added the STS to make a clear suspension or better suspension. Right? So that is the purpose. When you add the STS, that is a surface active molecule, it will provide the colloidal stability, and hence now those nanoparticles which were tend to fuse with one another in the absence of surface active molecules, now they are stabilized by the presence of the surface active molecules. Now the van der Waal interactions are no more predominant than that of the electrostatic interaction, because there is a bilayer created around each nanoparticle by the surfactant molecules. You see over here. So, if we add sodium chloride will not help to provide the colloidal stability, but we have to add amphiphilic molecule. Sodium chloride is not amphiphilic molecule. It is simply made up of two ions, oppositely charged ions, sodium and the chloride ions. So therefore they have no ability, any ability to provide the colloidal stability. But on the contrary, if we have the amphiphilic molecule with the long hydrocarbon functional group, that is the hydrocarbon chain, so that will provide a bilayer. You see the bilayer now? This bilayer is traced with the head group of the cation or the anion. Whatsoever is the ionic surfactant is there, that is the charge on the surface. Now this charge will not allow another similar gold nanoparticle coated with the bilayer to fuse with this, because the charge, similar charge, the same charge, the same kind of structure you would expect on another gold nanoparticle. When these gold nanoparticles, they come close to each other, the similar charges or positive charges are going to repel, and hence they are not going to fuse one another. These are known as electrostatic repulsion. You see, this is bilayer on one gold nanoparticle. This is bilayer another gold nanoparticle. This is positively charged if the surfactant or surface molecule is positively charged. Here also positive charge, so therefore repulsions are going to occur, and hence there is no way this gold nanoparticle fused with this, and hence you achieve the colloidal stability. This is what I explained from the DLVO theory at that time, right? So VR and VA. VR is the electrostatic potential, VA is the non-electrostatic potential. In fact, the two interacting gold nanoparticle. So it all depends on the predominance of one potential over the other, and whatsoever is going to win, they are going to decide the fate of the particle. So when you use the surfactant VR predominates over the VA, and hence the repulsive interaction set in, the potential energy instantaneously increases. This is the potential energy curve for the electrostatic repulsions. This is the potential energy curve for the non-polar water-wall interactions, attractive interaction, and in this case potential energy falls and lead to flocculation. You know the word flocculation or coagulation? So they are the irreversible process. When the coagulation among the gold nanoparticle or the nanoparticle particles happen, you cannot reverse it. It is an irreversible process. So this is what the solution you made yesterday by adding SDS.
And now each nanoparticle having the bilayer of the surfactant, and as you see, you have the bright blue red color,
and that provides you the absorbance sharply close to 520 nanometer. So this was the story for the gold nanometer. Now, what if I'm going to synthesize nanoparticle in the hydrothermal container? So I'm going to explain what is the meaning of that. The reaction which you perform this one, gold ions by treating them with sodium citrate or sodium borohydrate, the reaction which you performed in the lab yesterday. So that was a straightforward reaction occurring at the room temperature. And we have another reaction. If you take
iron sulfate, ferrous sulfate, ferric chloride, if you mix the solution of these two, and then you add ammonium hydroxide, that's the base, you can initiate the reaction to convert them into iron oxide, Fe3O4. This reaction can also
be performed at the room temperature. You don't need any kind of special experimental condition. But this will not produce the crystalline, well-defined iron oxide nanoparticle unless after completing the reaction you are going to place it in the steel container, including the Teflon container placed in a steel jacket. So here is the Teflon container. Teflon is non-reactive, and here you have the steel jacket, and there is a steel cover. You can tight it. You perform the reaction at the room temperature. You pour the contents into the Teflon container, tight it. Now you place this at 150 degrees centigrade for 24 hours. Placing it at 150 degrees centigrade for 24 hours, it is not the purpose to complete the reaction. The reaction is already completed. But to perform the crystallization of the iron oxide nanoparticle. So when you perform, apart from this, three components, iron in oxidation 2, iron in oxidation 3, and the base. The fourth component is always surfactant, that is not shown over here.
Because that is not participating in the reaction, it only provides the colloidal stability. So that surfactant is here in the form of a bilayer. Now, though I have shown the same color of the nanoparticle, you could assume that is not the gold nanoparticle, they are the iron oxide nanoparticle.
The iron oxide nanoparticle produced over here, I have shown over here. Now, what happens after this? When I place it in the oven at 150 degrees centigrade for 24 hours, the iron oxide nanoparticle, which were not of same shape and structure or the size, when the reaction is performed at the room temperature, but when you are going to perform in the reaction vessel at elevated temperature and obviously elevated pressure, when when this is going to heat up, the pressure inside the Teflon container will be much higher than the pressure outside. So we have here it is 1 atmosphere pressure. So what the pressure is going to do, or the elevated temperature is going to do, to alter the physical properties of the nanoparticle. That is the purpose of our understanding in this lecture. This kind of treatment is known as hydrothermal. Hydrothermal means that we have the reaction that has taken place over water formed in the atmosphere. Thermal at elevated temperature. So under high temperature pressure condition. So this kind of treatment cannot be performed in glassware containers, because you are going to increase the pressure to a very high degree. So therefore, the reaction cannot be performed in glass container, so it has to be a steel. The picture of the steel container is here. It is shown like this. It's something like this, quite a big container like this. This rod is to open the lid. The lid of the container is this much big, and you have to put pressure in order to open it. And inside it's a very heavy steel jacket. Inside it is a Teflon container and the reaction bombs. So instead of using the STS in this reaction or any kind of conventional surfactant, if you use, remember I told you that what is the Gemini surfactant in the beginning of the lecture? If you use this kind of surfactant, the double tape and the double head group, ammonium head group with the bromide counterion, ammonium head group and the bromide counterion. When you use a Gemini surfactant, schematically you can show it like this. A very strange thing happens. The nanoparticles which were suspended in the aqueous bond, if we use a conventional surfactant, but carefully choosing a Gemini surfactant, the nanoparticles are adsorbed at the interface. This is a solid liquid interface. This is an air-water interface. You see, there is no nanoparticles suspended in the aqueous bond. All nanoparticles are continuous. What is the meaning of this? If you take them out after the annealing, when the crystallization is completed, after 24 hours, you Teflon container you can take out, you place the magnet, all nanoparticles are attracted towards the magnet, right? So, here, this is the magnet, this is the nanoparticle suspension. It is water soluble, not surface active. When you place the magnet, see all nanoparticles are attracted towards the magnet. So this will happen. Now when you have this kind of situation, right, and you can simply remove all nanoparticle from the container by applying the magnet, removing the aqueous phase that contains excess of Gemini surfactant. You can purify it with fresh water, and when you are going to suspend it in the atmosphere, they are going to arrange at the interface. They will never go into the atmosphere. They will not go into the atmosphere. Such kind of particles are known as surface active particles. Now, what is the difference in the actual sample of the surface active and the bulk soluble iron oxide nanoparticle? This is the bulk water soluble iron oxide nanoparticle. When you do not use the Gemini surfactant, when you use only the conventional surfactant, this is the water soluble, and the color of the sample is close to brown color, yellow brown color, because of iron oxide. It's a rust color.
Rust color is the same thing.
Right. The surface active, they are not suspended, they are only, you see the black band? The black band consists of very tiny particles which are only arranged at the interface. If you pick them to prove that they are indeed surface active, you can suspend it into a solution of biphasic solution of organic and aqueous. You can choose any organic solvent which is not miscible with water. So there are plenty of organic solvents which are not soluble in water. Benzene is one of them, right? And when you, or hexane, when you place the surface active iron oxide in such a basic biphasic solution, you will see they are not going to either absorb over here or in the aqueous bulk or in the non-aqueous bulk. They are exactly at the entrance. You see the black line, the black band, that is where all the iron oxide nanoparticles exist. Any question up to here? If you have any confusion, you can go ahead and ask me.
Okay.
Now, somebody can ask you, yes, I can see this band of small particles, but
Can't I see the real picture of the particle? Yes, you can see. Here is the real picture.
They are
The iron oxide carrying Fe3O4 nanoparticle.
You see over here,
Right? It is 50 nanometer scale bar,
it's
20 nanometer scale bar, because from low resolution we are moving higher resolution and even much higher resolution.
5 nanometer scale bar. You see only 3 particles. They are the iron oxide. You could see the crystal planes. You see the exactly the way we have the fingerprinting, the lines of the skin, the cells. Exactly, you have the atomic lines over here, and they are the crystal plane. Those crystal planes.
I remember I told
you there are
three different predominant
kinds of crystal plane.
111,
100, 110 crystal plane. So these are the lines of the atom, because it's 5 nanometer. So this is the half of this is 2.5 nanometer, then the half that is maybe 1.7 nanometer, just close to 1 nanometer. So in this way we can see that it's a very high resolution image. And the white arrows indicate the coating of the Gemini surfactant that provides the colloidal stability. So there is a you see there is a thin layer of the coating that is provided by the Gemini surfactant. And this is the X-ray crystallography to demonstrate the crystal structure. We don't need to go ahead in this, but I'll explain that what kind of crystal structure you could expect. So these are the surface active iron oxide nanoparticles. Now what they do very remarkable things. So microscopically, this layer, how this layer provides the surface active. Actually, the thing is now we want to know that how these iron oxide nanoparticles, they become surface active. How the property of surface activity is induced or introduced by which kind of chemical functionality these nanoparticles are possessing. So I am simply taking up, it's a part of the surface of the nanoparticle, and this is the way the Gemini surfactants are arranged. Each surfactant, so a molecule possessing 2 hydrocarbon tails, and the hydrocarbon tails are entangling with the adjoining hydrocarbon tails from the other molecules. It is forming a bilayer. Eventually I have shown a monolayer, but bilayer, and then provides a colloidal stability. What happens when we place this structure at elevated temperature and pressure? I am talking about this one. When I place this at an elevated temperature and pressure, how I can achieve the surface activity? So when I increase or when I perform the hydrothermal treatment, these hydrocarbon chains become much more hydrophobic. How? Because this is the polar head group. There is some degree of water molecule close to
the polar head group. But when hydrothermal treatment is provided,
all
the water molecules are expelled
and the environment over here becomes very intense non-polar environment. What if I have the longer spacer? This is the spacer. We call this as a spacer, which connects the two identical parts of the molecule. If we have another Gemini surfactant with a longer spacer, so that folds between the hydrocarbon tails. Bottom line, you could have a different kind of Gemini surfactant, but not all Gemini surfactant provides the surface activity or produce surface active nanoparticle. The problem, where is the problem? The problem is that if you introduce a longer spacer, that reduces the compatibility of the hydrocarbon tail and reduces the steric hindrances. If you have a bigger head group, so that also increases the distance among the hydrocarbon tails and reduces the non-polar interaction. So therefore all those factors which reduces the hydrophobic interactions between the non-polar tails, they are contrary to the surface active effect. So remember I told you the HLB scale that runs from 0 to 80. When you have appropriate Gemini surfactant that could impart the HLB scale close to the number 7 to 8, then the particle becomes surface active. The way I told you over here that a surfactant, surface active molecule, when the polar and the non-polar functional groups, I mean the compatibility that provides the amphiphilicity somewhere up close to HLB number this becomes surface active, not this, exactly the same way. So the nanoparticle that is coated with the Gemini surfactant, if you choose appropriate Gemini surfactant, and that provides the surface activity or the surface activity HLB number value close to this, then the nanoparticle becomes surface active. Neither this particle with the higher HLB number or the lower HLB number is going to be surface active. So it is not the surface activity of the particle. In fact, it is the surface activity provided by the Gemini surfactant molecule, surface active molecule. But they are absorbed on the nanoparticle. So therefore the total surface active, the total entirety, individual entirety with the layer of the surface active molecule becomes a surface active entirety, and whose HLB number, if resides somewhere over here, the whole entirety becomes surface active. You got more point? This is the story behind that. And here is another very high resolution image showing you the adsorbed Gemini surfactant on the nanoparticle. If the scale is 10 nanometer over here and the particle is close to 50 nanometer, you see the lines. These are the lines of the atoms arranged on a crystal lattice, right? So we can identify that from the spacing and to find out that which crystal plane this is. Now we are going to put them in practice. What they can do. First, macroscopically, we know that the surfactant, the polar head group is in the aqueous phase, aqueous and air. The tails are in the air, right? We know that. But how can we show the surface activity exactly the way we show here for the surfactant molecule for the surface active nanoparticle? Now, it is slightly complicated to understand how the surface active nanoparticle is arranged exactly at the air aqueous interface. Air is a non-polar, so therefore non-polar part, non-polar environment can only accommodate the hydrocarbon tails, not the polar heteron. So therefore, the molecules which are adsorbed on the surface of the particle, they should have only tails directed towards the aqueous phase. But these tails cannot be directed towards the air phase, but these tails cannot be directed towards the aqueous phase because they are non-polar. So therefore there is another layer of the particle. This is bilayer, this is monolayer. So this unique kind of molecular arrangement of the Gemini surface active molecules will make the whole entirety of surface active. So you see that they are arranged at the interface or over here. In this Y, the particles over here, here and here. What is this? What we did actually, to show the application of the surface active nanoparticles, iron oxide nanoparticle, we took different concentration of the gold nanoparticles as pollutants. You may assume that in a glass of water there are suspended pollutants of particles. You cannot see them because they are in nanometer range. So you could see that the water is clear, so therefore it's clean, but in fact it is not. We took the model gold nanoparticle because a very low concentration of a gold nanoparticle generates a color. We increase the concentration of gold nanoparticle in this solution on this way. So this is the dilute concentration, higher, and maximum concentration. We took the 4 concentration of the gold nanoparticle suspension. We added the constant amount of the surface active nanoparticles above it, and we waited for a few hours. After a few hours, we saw the first 2 solutions are completely clear. Their color reduces, but the color remains. It means that all gold nanoparticles in the first 2 solutions, in the first 2 concentrations, they are taken up by the surface active molecules, surface active iron oxide nanoparticle. But here, the iron oxide nanoparticle concentration is not sufficient. So hence, the excess amount of gold nanoparticle as metallic pollutants, so that remains in the solution. How do we know that the gold nanoparticle as pollutant, they have really taken up by the iron oxide nanoparticles? What we did, we picked this sample, expecting that it is the combination of iron oxide and gold nanoparticle sample. We extracted from the solution. It all happens like this. Gold nanoparticles were attracted to that of the iron oxide nanoparticle. Complexation occurred. We placed the magnet, removed the entire sample. Remove the entire sample and look through the electron microscope. See over here. You have low contrast particle, you have very high contrast particle. It means that at least the low contrast particle, they have the different chemical composition into high contrast particle. When we perform the mapping, we call it mapping. So here we call it is EDS, it is energy dispersive spectroscopy. If you look at it, is basically the photoelectric effect, and it's a first year chemistry. So this facility is included in that instrumentation, and it can only look for, if you tell that we want to see only the gold nanoparticle, so then you will see only the gold nanoparticle. So the emission which is coming out, electron diffraction, electron emission that is happening from the valence electron cloud. So that is the binding energy or the energy consumed that is proportional to that of the gold valence shell. So therefore here in this image you see only the gold nanoparticle. So it means that this bright group of the particle is because of the gold nanoparticle. And why it is more brighter? Because the transition metal diffraction is much more intense in comparison to oxide metal nanoparticle electron diffraction. And when you perform the iron mapping, as you could see the all other particles, so there is one iron component, and likewise you can have the oxygen component or any other component as well. So we took one sample from here, and this confirms the presence of gold nanoparticle which were extracted from here. We took another sample and performed the same way, and here we prove that there is also gold nanoparticle. Greater amount of the gold nanoparticles was the higher concentration you see over here, and the iron oxide. So this is the EDS spectrum which explains which elements are present in the sample. So you can simply see it over here quantitatively. What is the meaning of this whole story? The meaning of this whole story is, instead of using the filtration process to clean the contaminated water, you can use this is much more easier technique. Right? You don't need any filtration process. Simply place the magnetic surface active magnetic nanoparticle sample on the surface of the contaminated water, and your all metallic pollutants, they are going to be attracted towards the sample, and this way you can purify the contaminated water. Where you could expect such kind of contaminated water, all mining industry, iron ore industry, steel industry, so they have the industrial effluents, they possess a very high degree of concentration of suspended metallic particles. Okay, so there is another case over here. It is not simply the blank gold nanoparticle. In order to allow them to be attracted or pulled by the iron oxide nanoparticle, so you have to have the opposite electrostatic interaction. It means that the surface active nanoparticle, if the head group is positively charged, you will be using the stabilizer, colloidal stabilizer, with predominantly negative charge. So these are not the magnetic field because of which the transition metal is going to be attracted with the iron oxide. That's not the case. These are the electrostatic interaction. Then what is the advantage of this? The advantage of this, you are not performing the filtration in anywhere in this case. Simply putting the magnet over here will allow to remove all the pollutants. In conventional purification, so you use the filtration, a very complicated process, but in this case, this is a modern technology. So you will see now, in future, you will have modern technology which can be used for the purification of water without the filtration, and they are much more efficient. So, at the end, surface active magnetic nanoparticles, a new class of nanomaterials with interfacial application. I have shown you just one application, but there are many other applications. I show you other biological application in the next lecture. Since I wanted to first give you the example of the conventional application, which is more easier to understand, right? And it is much more straightforward. Why we need the surface active magnetic nanoparticle for the purification of water, right? But after that, you will see that we are going to apply, we are going to use the surface active magnetic nanoparticle for biological applications. They remove pollutants without incorporating in the atmosphere. You see, they are removing the pollutant, but they are not incorporated in the atmosphere. They remain at the interface. That is the beauty of surface active iron oxide nanoparticle. Otherwise, there are other chemical methods where you are putting the chemical. Chlorination is one of the process where you have to kill the harmful bacteria in the water. So, and you have to flush the chlorine through the water, and then when you fill the glass of water at home, so you see the air bubble, and you have to keep it just for a few seconds so that all the bubbles are gone, and then you are going to drink it, right? So I mean to say that for any kind of purification treatment which you are going to apply in order to clean the contaminated water, you have to apply the treatment inside the aqueous bulk of the contaminated water, But this is not the case. Here, the treatment is simply applied from the air-water interface rather than putting the magnetic nanoparticle in the aqueous bulb. No filtration process is required to remove pollutants. Application of external magnetic field. So no filtration process is required, that you have seen. Application of external magnetic field can remove pollutants, loaded magnetic particles. Now, the uniqueness, why we have specifically used the magnetic nanoparticles, surface active magnetic nanoparticle, the reason is the removal of the magnetic nanoparticle from the interface is much easier. What if they are not magnetized? So then, what we have to do, we will need to perform the filtration or the centrifugation process. But in this case, you can simply avoid these complicated processes. Place the magnet, collect all, and remove the water, or clean water. So that is the advantage of the surface active nanoparticle. So this is all about the story which we have begun today for the surface active magnetic nanoparticle. We will continue with this. Hopefully you have understood. Thank you so much for your attention. And now you can ask me if you have any question.
There will be a tea break. And after that tea break, we will assemble here only for the instructions of
synthesis, characterization, and electronic properties of
gold and silver nanoparticles. Actually, this has been designed beautifully by
Dr. Bakshi and Dr. Jasprit Kaur. So all the experiments are interlinked. So whatever we have done in the second experiment is purification and characterization of Gemini surfactants. We have synthesized the Gemini surfactants. Those Gemini surfactants we will be using today for the synthesis of iron oxide coated nanoparticles. So the nanomaterials, the materials at least one dimension in nanometric scale are nanomaterials. They have dimensions from 1 to 100 nanometer. Next. So these are this is the classification of the nanoparticles: 0-dimensional, 1-dimensional, 2D, 3D. Next. So there are various synthetic approaches. One is top-down approach and the bottom-up approach. So synthesis of iron oxide nanoparticles, this can be done by physical methods, chemical methods, or biological methods. In the physical methods, we will discuss the ball milling, the laser-induced pyrolysis, and in the chemical methods, we will be discussing the hydrothermal and co-precipitation. Then in the biological methods, it is plant-mediated and bacteria-mediated. So in the ball milling, the nanoparticles are produced through the approach. So this is through the mechanical addition. Now the nanoparticles, the core particles, they are introduced in a rotatory drum, and the different size of the balls are also introduced, and it is rotated. So it will give different sizes of the nanoparticles. The sizes will differ. It will be not of the same. The sizes are different. Next. Then second is the laser-induced pyrolysis. So in this figure, this is your instrument for this pulse laser. This figure presents a schematic diagram illustrating the fabrication of iron oxide nanoparticles using pulse laser-induced pyrolysis method. This process mainly entails adding H2O2 to ferrocene and acetone precursors, then initiating a photolysis reaction using the energy from pulsed laser light. Additionally, the figure includes a formula displaying the suspended nanoparticles. This
photograph is showing the suspended nanoparticles, both with and without magnetic separation. So there is a magnet, so magnetic separation is there. Next. Now this is the method we will undertake today. So in the lab we will be doing the hydrothermal method. So a total of 20 ml of fraction mixture containing 4 milliliter of millimolar of FeCl3 and 4 millimolar of FeS4 in 1 ratio to 1 mole ratio along with required amount of GIAN surfactant. The GIAN surfactant that we synthesized in the second practical, and ammonium hydroxide are taken in Teflon container that is further sealed in a steel jacket and placed at constant 150 degrees centigrade for 24 hours. The reaction mixture must obtain is cooled to room temperature and samples are purified repeatedly from hexane.
So this reaction is base catalyzed. Now to form the nanoparticles, what is the requirement, basic requirement? What is needed? You have metal salt, then you have reducing agent and the capping agent. So this is the basic requirement. But in this case, this reaction is base catalyzed. Okay? So no reducing agent, it is base catalyzed reaction. Next, please go back. So this reaction we will be carrying out in this Teflon flask. This is the Teflon container already explained by Dr. Bakshi. Okay? And this is the steel jacket. It will be inserted inside this steel jacket, and it will be the reaction will be carried out at 150 degrees centigrade for 24 hours. This has already been explained by Dr. Bakshi in the previous lecture. So these are the magnetic nanoparticles. So these are rust in color. So this is the magnet. So it is going to the one side towards the magnet. So this is the co-precipitation method. So which method is the better one? Co-precipitation or hydrothermal? Dr. Bakshi has just explained. Hydrothermal, okay? It is carried out for 24 hours, okay? And this takes place almost instantaneously. So the ferric chloride and ferrous sulfate, okay? So this is added in a flask, 3-neck flask, and in the nitrogen atmosphere, stirred for 30 minutes at 80 degrees centigrade. Then we add 1 molar sodium hydroxide solution, and then we add 12 to 12 GIAN surfactant, and this will be formed after 12 hours. We keep it for 12 hours. Then next is the biological method, physical, chemical, and third one is the biological method. So we take the leaf, we can take leaf, or we can take fungi. Okay, so what is the active material in leaf or fungi? There is some active material. Phytochemicals in leaf and in fungi or yeast or bacteria. It is enzyme. They act both as reducing agent as well as capping agent, right? So we add to the iron precursors, we add leaf extract, and it will form iron oxide nanoparticles. So the magnetic property of Fe3O4 nanoparticles, magnetite exhibits ferrimagnetism, where the magnetic moments of ion in different sublattices align in opposite direction but with unequal magnitudes, resulting in a net magnetic moment. It consists of Fe2 positive and Fe3 ions, with Fe3 ions occupying and octahedral sites, while Fe2 positive ions occupy only octahedral sites. This unique arrangement leads to a strong overall magnetization. Fe3O4 is known for its high Curie temperature and is used in the magnetic applications such as magnetic recording and ferrofluids. Now this will be explained in the next lecture by Dr. Bakshi. how it is occupying the both tetrahedral and octahedral sites. I have gone through the slides of Dr. Bakshi, so he will be explaining this. So iron oxide nanoparticles, they have magnetic properties. So what type of magnetic properties they have? They are super paramagnetic. So I will shortly explain why they are super paramagnetic. They have catalytic activity. They have environmental applications. In the in the tomorrow's practical, we will discuss the environmental application. Then easy functionalization, electronic properties, stability, and cost. Next. So what are the biomedical applications of iron oxide nanoparticles? Targeted drug delivery. Iron oxide
Nanoparticles are used in targeted delivery due to their magnetic property, allowing precise control and delocalization of therapeutic agents.
Then it can be used in hyperthermia. What is hyperthermia? This is the iron oxide nanoparticles are commonly used in hyperthermia therapy where they are generated localized heat to destroy cancer cells. So these magnetic nanoparticles are taken to the cancer cell and magnetic field is applied where there will be generation of heat. So this cancer cell will be destroyed when it is exposed to alternating magnetic field. Then it can also be used as MRI contrast agent. Fe3O4 nanoparticles are commonly used as MRI contrast agents due to their strong magnetic properties, enhancing image contrast. Now, what is the function of this iron oxide nanoparticles? How they act as the contrasting agents? They will produce the contrast. They will be producing the dark field. Okay, so the tumor will appear as bright, other portion will appear as dark. Okay, that is how it is acting as MRI contrast agent. So characterization of iron oxide nanoparticles by PXRD, FTIR, HRTEM, FESM, and UV visible spectroscopy. So this is the PXRD of iron oxide nanoparticle without coating that we have synthesized in the lab. The prominent diffraction peaks are observed at 30.1, 35.5. So these correspond to 220, 311, 411, and 450 planes. The sharpness and intensity of peaks indicate high crystallinity and phase purity of the synthesized iron oxide nanoparticles. During the last lecture, Dr. Bakshi explained the PXRD with the coating of the surfactant. Next. So this is FESM of ferrous oxide nanoparticles. So in the aggregated form, the technique allows visualization of Fe3O4 and nanometer scales, showing its crystallinity and uniformity. FSM images typically show Fe3O4 particles as agglomerates or individual nanoscale spheres, depending on synthesized methods. So this is without coating. So that is why it is shown as agglomerated, right? So this is the EDX of Fe3O4 nanoparticles. So those types of iron and oxygen is also there. Then FTIR of Fe3O4 nanoparticle. It shows characteristic absorption band due to its vibrational modes of iron oxygen bond. So the characteristic peaks are at 550 to 400 due to FeO stretching vibration and broadband at 3400 to OH of water. This is OH of water, right? Now HRTM of this Fe3O4 nanoparticle This is the high resolution TEM image showing the crystalline structure with spherical shape of Fe3O4 nanoparticles. It provides insights into the material's morphology and nanostructure essential for magnetic and
catalytic applications. So this
this
is
is
the
the
UV
UV
spectra.
spectra.
So
So the peak, the absorption peak you will be getting at 300 nanometer. This is associated with Fe3 positive O2 negative charge transfer. This is ligand metal charge transfer transition. Next. So ferrous Fe3O4 nanoparticles were successfully synthesized with Gemini surfactants. The Gemini surfactants provide enhanced colloidal stability to Fe3O4 nanoparticles, preventing aggregation. The techniques used for the characterization XRD, TEM, FTIR, EDX, and UV visible spectrophotometer. Next. Jotted down some slides uh, to explain the superparamagnetism of the nanoparticles. So, what type of magnetism is there? Diamagnetism. Okay. In the diamagnetism, the electron is fully filled in the shells, so atoms have no magnetic moments. So it will be having very small magnetic susceptibility. This is graph between magnetization and applied magnetic field. So it will be having very small susceptibility. Then paramagnetism, uh, all the magnetic moments are randomly oriented. They are in all the directions. It is having very small magnetic susceptibility. Then ferromagnetism, these are parallel aligned. So these are all in one direction. So this is having large magnetic susceptibility. Then antiferromagnetism, it is aligned. It is having mixed parallel and anti-parallel alignment of the magnetic moments. So they will cancel out. Net is zero. So it is also having very small magnetic susceptibility. Then the ferrimagnetism. So this is again mixed, but mostly in the one direction. So this is in one direction. This will cancel out. So net is, it will be in the one direction. So it is also having this magnetic susceptibility, but in this case it is smaller than this one. Ferromagnetism is having the highest. And you remember that paramagnetism, it is randomly oriented magnetic moments. Next. This is the magnetic hysteresis curve. So how this magnetic hysteresis curve is drawn? What is the instrument used? This is VSM, vibrating sample magnetometer. So this is the magnetic hysteresis. So at this point, we are having the magnetization is zero. So if we apply the magnetic field, this will go on increasing till this point. This is MS. MS is saturation magnetization. This corresponds to this. So this is the saturation magnetization. Now, if we decrease the applied magnetic field, so it will not become zero, but it will be MR. MR is remanent magnetization. Some of the magnetization will remain. That will be remaining. That is your remanent magnetization. And if we further decrease the applied magnetic field, means it is in the opposite direction. If the magnetic field is in the opposite direction, then this will be HC. Applied magnetic field will be HC. That is, this will be coercive magnetic field. Right? So these materials, they are having high remanent magnetization or coercive magnetic field with further decrease in the reaction, it will reach at this point. This is again the saturation magnetization, but in the opposite direction, in the negative direction.
And if we start increasing, then
Then we will again reach here. This will be the
saturation
magnetization, right? Please go back. So the materials like the permanent magnets that are magnetically hard, these materials are known as magnetically hard. They have high MR. MR is high MC, high HC. This is H.
This is having high HC. Both of them is high. Okay? So magnetization remains after field is switched off. When we switch off the field, it will remain. That is magnetization will remain there. Okay? It is having high MR and high HC. Both of them will be there.
But in the soft magnet, what will happen in the soft magnet? This will come, this will be having low
MR and low HC.
both of them will be very small.
Because this happens in case of magnetic nanoparticles. Okay? What should be, how this curve should look in that case? उसमें कैसा होना चाहिए? What should be the shape in which this passes through the origin? Then only MR will be small, HC will be small. Okay? So in the magnetic nanoparticles, it should be passing through the origin or it should be very small. Next. So superparamagnetism, the magnetic iron oxide nanoparticles are superparamagnetic.
In nanoparticles, thermal energy is sufficient to overcome the spin-spin exchange coupling energy at room temperature. So these are the magnetic moments.
In case of
Ferromagnetism, the materials showing ferromagnetism,
there will be no exchange. See the diagram. When the particle size is large, right? So the exchange energy, this barrier is high. This is the room temperature. This barrier is high. Okay? So there will be no flipping of the magnetic moments. That is in the ferromagnetic materials. But with the decrease in the size of the nanoparticle, so this is the energy barrier. So it is below the room temperature. So there will be flipping. If there is flipping, this means that it will be randomly oriented. It will be randomly oriented if it is flipping. Right?
So this approach is paramagnetism.
Please go back to previous again. So what is paramagnet?
Randomly oriented magnetic fields. That is why it is known as
superparamagnet.
right? Okay, thank you very much.
So we will now proceed. Please see this formula. You can make the calculations. M is the molarity. It is number of moles of solute divided by volume of solution in liters. Right? You have to make 20 milliliters of the ferrous sulfate and ferric chloride solution. So 20 into 10 raised to power minus 3 molar. This is equal to, what should be the number of moles? This is given by WA by Avogadro's number, WA by the molar mass into 1000 divided by Vs. This is in milliliter. BS is in milliliter. So please do the calculations. What is WA? This is X. M is for ferrous sulfate. This is 278.02. For ferric chloride, this is 162.21. So X divided by 278 divided by 0.2 into 1000 upon 100. You have to make the 100 ml solution. So what is the value of X? Please calculate the value of X for this ferrous sulfate. Then for ferric chloride, here you put 162.21. Please do the calculations. So what is the result? 0.5560 gram in 100 ml of distilled water. This is for ferric chloride. Point 3244 gram in 100 ml of distilled water, right?
Yes, sir.
So these solutions have been already prepared in this lab, right? Now you have to add 250 milligram of Gemini surfactant. What is your Gemini surfactant that you have prepared in your second lab? What is the name of that? 12. You have to add that 250 milligram. Then you have to add 4 milliliter of ammonium hydroxide. 4 ml of ammonium hydroxide. This acts as base. So this will be in the Teflon container. Please show me the Teflon container. So this is the hydrothermal process and this is the Teflon container. So all the contents will be put in this Teflon container, right? And then again it will be placed tightly in this jacket, and it will be kept in the muffle furnace at 150 degrees centigrade for 24 hours, right? So please, there are 3 jackets and you can do the experiment. कैसे बनाए
कोई बताओ निकालते हो ना तीन नोट्स बनेंगे जगह पे 4 नोट्स होंगे 4 से जगह
Now, it is enemy secretary is dissolving heat and distillation. Motion. And this is your ammonium hydroxide. Each of the hydrogen four ml. इसमें डिस्टिल वाटर ना सबसे लास्ट में जब ये अच्छे से डिजाइन हो जाएगा ये इसके अंदर ऐड करना है कॉटन की भी और उसके बाद
स्टडी करनी है तो मैग्नेटिक फील्ड
ताकि वो अच्छे से डिजॉल्व हो जाए और जैसे ही डिजॉल्व हो जाएगा और उसके बाद स्टील में रख देना और उसके बाद ओवन में रख देना 150 डिग्री सेल्सियस पे 4 Let's do water.
टेम्परेचर देना है तो हम इस पर भी डायरेक्ट टेम्परेचर देंगे तो ये हमारा वेपर क्या है कि खराब होने का बिल्कुल होती है। तो इनको क्या करेंगे तो प्रेशर भी कंट्रोल करना है। अभी क्या जैसे कि प्रेशर बनेगा तो उसको कैच कर सकता है, ठीक है। जब हाई प्रेशर होगा तो कैच बाहर आ जाएगी, इसलिए हम क्या करेंगे ये पूरा सेटअप को ये मतलब बोलते हैं, ठीक है। ये कंटेनर और ये पूरा सेटअप क्या होता है सारे चीज़ों को पूरा करेंगे और उसको इसमें क्या करेंगे पैक करेंगे। पैक करने के बाद हम इसको वोटेर में उसको पैक करना है, पैक GIAN में लिखी है, GIAN में कितना लेना है पूरा ले पानी में नहीं बबल को नहीं
मैं फिर हूँ जा रहा हूँ नहीं फिर मैं फैमिली बेस पाया फिर रिएक्शन ब्लैक सोल्यूशन
हाँ जी, कलर चेंज हुआ था।
हाँ, तो वो रिएक्शन तो हो जाता है, बट क्रिस्टलाइजेशन जो है ना वो होगी जब इसको आप रखोगे 150 डिग्री सेंटीग्रेड पर।
ये टाइम ऑप्टिमाइज किया हुआ है।
ये टाइम ऑप्टिमाइज किया हुआ है
सारे रखे
हाँ हाँ उसी तो पिछले सिंपल 8 साल तो कभी इसी सर्विस
कर दिया। हाँ रख देते हैं।
बाकी साइड पे होगा कैमरा
रखोगी एक एक करके कैमरा एक और जरा आगे आने को। That was prepared earlier. Okay, only without coating, iron oxide nanoparticles without coating. Okay, you can see the.
ऑयल
भी अच्छे से करना।
ये सुविधा है
कितनी है ये? लैम्डा मैक्स इज 460. हाँ शेयर करो उसको, एक्चुअली शेयर करो, उसमें अपने आप सेलेक्ट करेंगे, ठीक है ना, वो करो. So you have to calculate the lambda max and epsilon maximum. You know the UV spectrum? आपने किया Woodward-Pfizer rules? You know Woodward-Pfizer to calculate lambda max? ठीक है ना, वही इसमें क्या आएगा, there will be lambda max, okay, that is at 416 nanometer lambda max, and epsilon max is at 2.6635. That is the absorbance or epsilon. That is also epsilon. ठीक है, आप इनको करके दिखाओ, ये बच्चे अपने आप करें दोबारा हो सकते हैं. यहाँ से what type of hysteresis group is expected for magnetic nanoparticle? R2PM. What type is expected? That is by VSM, जो मैं पूछ रहा हूँ, ठीक है ना? What type is expected? Hysteresis group, you have seen the hysteresis group. It should be passing through the origin, okay? So that it should have the minimum value of HC
and MR.
That should be.
ये आप एक्सेल फाइल से मैनुअली चेक कर सकते हो जहाँ पे आपकी अपलोडेड नहीं वही आपकी डी हो गई।
In aqueous medium. In aqueous medium. So students, you can see you have synthesized gold and silver nanoparticle that you synthesized in yesterday's practical. Okay, in aqueous medium. So these are the gold and silver, right? So these are the magnetic nanoparticles that we have synthesized today. वैसे तो उसमें रखे हुए हैं, पहले हमने बना रखे हैं, ठीक है? So we will be adding this to this. This is in hexane. So there will be two layers, right? And there will be extraction of gold or silver with the help of this nanoparticles. Okay? So that will be your tomorrow's practical. Okay.
Yes, all the participants. Now you can have your lunch. Your next lecture will be at 3 in the NCN hall.
Good afternoon. We are going through the next lecture, lecture number 9.
So we are dealing with the
Iron oxide nanoparticle. Again, the characterization of biological properties. In the previous lecture, we understood that how we can apply the synthetic synthetic reactions in order to produce water soluble and surface active magnetic nanoparticle. Uh, Now we will try to understand that we can go ahead with some of more characteristic properties of these iron oxide nanoparticles along with the biological applications. So I showed this slide, and this was basically for the synthesis of the iron oxide surface active nanoparticles. I told you that if we are going to use the Gemini surfactant over here, and we can produce the surface active magnetic nanoparticles. Try to understand the application of this surface active magnetic nanoparticle for the purification of contaminated water. Now we will go ahead with applications. This was in all the, why I'm repeating this slide, the reason is that in all the applications, whether we are using the surface active magnetic nanoparticles or the water soluble magnetic particles, the size of the magnetic nanoparticle is around 20 to 25 or 30 nanometer. And the applications which I'm going to show you, whether those applications belong to the water soluble magnetic nanoparticle or the surface active magnetic nanoparticle, all applications are being carried out by the similar kind of shape and size of the iron oxide nanoparticles. Now, since they are highly susceptible to the magnetic field, as I told you in my previous lecture that the main advantage of the surface active magnetic nanoparticle is that when we are replacing or extracting the nanometallic pollutants from the contaminated water, we do not need the filtration process or the centrifugation process, because the nanoparticles, these nanoparticles, they have very strong affinity to be attracted by the external magnetic field. So I mean to say that if you are going to bring the external magnet close to the container, all the magnetic nanoparticles which are carrying the pollutants now, so the complexed nanoparticle, which is the combination of iron oxide nanoparticle as well as the pollutant, everything can be extracted simply by placing the magnet to the side of the container. So I am going through some of the tentative information related to the magnetic field or the magnetic field generated and why these iron oxide nanoparticles are susceptible to the external magnetic field. So we will go through some of the preliminary characteristic properties as well as the crystal structure. Since the magnetic nanoparticles, whether they are water soluble or they are surface active, the composition of iron oxide is Fe3O4. So we'll try to understand that under what circumstances we are going to have this composition of the iron oxide in magnetic nanoparticles. Since the purpose of this lecture is not to go ahead with in-depth analysis of the magnetic properties, because that is not the purpose. The main purpose is we have synthesized from the chemistry perspective, and then we have used it for various applications. So therefore, the other aspects which lead simply beyond the expectation of the chemistry students, so we are not going to focus on that, but I should give you some of the preliminary information. This is the unit cell of the iron oxide nanoparticle. This is something unique unit cell, because you have seen when we were talking about the characteristic properties of the crystalline solid, at that time we talked about the definition of the unit cell. But the unit cell we explained in those slides in that lecture So that is contrastingly different from this unit cell. The main thing was that in that unit cell, we were talking about the single cation and single anion, and that was the salt. This is oxide, that is not a problem. Here, it is not one kind of cation we are going to talk about. There are two kinds of cation. The one is in oxidation state 2, another one is oxidation state plus 3. So the bonding structure of the oxidation state 2 and oxidation state 3, that varies in this lattice. The positions which the oxide ion is taking, so those are much easier to understand. You will see that the gray balls, so they are the oxide ions, and they are taking the face-centered cubic position. So there are 8 oxygen over here, 4 and 4 below, and apart from 8 there are 6 on the faces, so 14 oxygens total. The thing is how we can quantify the formula, the way we quantified the formula of the ionic compounds in that lecture. You will see that now, instead of a single unit cell, there are several other cage structures. So you could see 1, 2, 3, 4 in the upper layer, as well as the 1, 2, 3, 4 in the lower layer. Now, why can't we show the unit cell in just one cage, the way we explained in our previous lecture? The problem is there are different kinds of bonding. Uh, this is very complicated, containing all the iron in 3 oxidation state ions, iron in 2 oxidation state ions, and the kind of geometry they are going to create when they are going to bind with the various oxide ions. Here I have shown only two kinds of the geometries by which the iron atoms are bonded to the oxygen atom. The one is this octahedral. Can you identify this is the octahedral shape? For the octahedral shape, actually there are 6 positions, 4 on the equatorial plane and 2 on the axial position. But all the 6 positions, so they have the bond angle 90. It's a uniform bond angle, and therefore this is octahedral arrangement between the iron and the oxide ions. So here there is a clear depiction that which iron ion is undergoing the octahedral kind of arrangement, and the which one is going to tetrahedral kind of. This one is tetrahedral. You clearly see that this iron ion is bonded to the oxide ion, so that is in the tetrahedral position. Suppose if I do not show the octahedral or the tetrahedral position, and simply if we have to focus on the size of the species or the ions, those are present in the unit structure. Is there any way you can differentiate between the anion and the cation simply from the size? In other words, if somebody asks you why the oxide ions having the bigger size in comparison to Fe3 ion or the Fe2 ions, you see, is there any particular reason why we have kept the size of the cation smaller than that of the anion, or simply it's a drawing? This is first year chemistry. First year high school chemistry, where you undergo the definition of ions. What is cation, what is anion, and what compels the neutral species, neutral atom, to convert into cation, and how the neutral atom converts into anion. And by doing so, how the size of the cation and the anion is going to be different from that of the neutral atom. Okay, let me say we have a sodium atom, we are taking the example of sodium chloride. Here I have the sodium cation. So I'm simply showing the positive charge over here. Okay, rather than this, just a minute. So what is the atomic number for the sodium? I think it's 11. How much? 11, correct, okay. So it means that there are 6 protons and 6 neutrons. Obviously, there are 6 electrons. Am I correct? It's a neutral, right? So now, if I have to convert into a cation, right? I should keep the slightly size smaller. No, 11. Sorry, 10. 11 proton. Sorry, 11 and 11 electron. Okay, yeah, this is correct. Now, in order to convert into cation, it means that it's a monovalent cation. I need to remove the electron, correct? So, if I simply say that this is the nucleus, which is made up of 11 proton and 11 neutrons, that contains the electron cloud over here is constituted by 11 electrons, correct? Now, when we are going to remove one electron, when the electron is being removed, it takes away not just one particle, it takes away equivalent to the electron cloud, right? Equivalent to that of one electron, the electron cloud is removed. So therefore, cation is smaller than the neutral species, right? Now I take chlorine. So chlorine, so there are 17, isn't it? 17 protons, 17 neutrons, and 17 electrons. It's a neutral, right? So it means that when I have to add the electron, it is becoming negatively charged, and the equivalent to one electron, the electron cloud is added, right? So therefore, A9, this is A9, this is cation. Cation is always smaller than its neutral species, neutral atom, and A9 is always bigger than the neutral atom because you are adding the. Now that is the case when we are comparing with the individual species, but when we have, and this explanation is not exactly the blanket statement, but most of the ions, cations and ions follow this. In other words, the anions are bigger than that of the cations. So the size of the gray balls has intentionally been kept much bigger than the size of the other, like black or the green dots. So they are representing that these are the anions. So I mean to say that wherever you see depiction of the lattice structure or the unit cell for any kind of salt or oxide, so therefore, if they are depicted the balls or the spheres, so you have to be clear enough that the bigger sphere belongs to the anion, where the smaller sphere belongs to cation. Okay, so it means that iron is here. It refers to the fact that this is cation of Fe, Fe2, Fe3, and this is also the iron cation. It means that all the peripheral positions are basically occupied by the oxide ions. That is fine. It's made up of 8 subcages. 8 subcages means there are one cage which encloses the octahedral geometry, other one tetrahedral geometry, and that moves like this. So therefore, there are 8 ways, 8 sub-unit cells, and you cannot pick just one to depict the formula for the iron oxide. So therefore, when you have to depict the formula of iron oxide, pick all the 8 sub-cages, and then
marking the boundaries of the
8
sub-cages.
sub-cages,
Here, the total number of atoms in the form of ions are included in just one
one
cage
cage,
in
in
order
order
to
to
avoid
avoid
the
the
confusion.
confusion.
So,
So
total oxygen
oxygen
atoms
atoms
in
in the form of oxide 32.
how
How
many
many
iron
iron ions in octahedral? 16 positions. How many iron in tetrahedral? There are 8 positions. So total 24 positions are occupied by the iron and 32 by the oxide. So can we settle to Fe3O4? The way we calculated the formula when we were doing the structure, unit cell structure for other ionic salts, and then we were trying to conclude that that unit cell structure is settling the final formula of sodium chloride, cesium chloride, or the salts which we talk about in that lecture. So here, what we can do, so there are now Fe 16 plus A 24 and 2. So in what way I can this reduce the number with the common factor. So it is 8. I can divide with the 8, right? So therefore 3 and 4. So this is the way we conclude the formula for the unit cell of iron oxide, right? So I mean to say it is slightly complicated to see over here because the drawing is not clear in what way we have the octahedral arrangement and in what way this is the tetrahedral arrangement. So it means that these interstitial spaces are in fact occupied by the iron ions in the oxidation 3, in the oxidation state 3 and 2. Now you see where are they reside in a one units in a one subshell. This one is the one subshell. So this one is Fe3 and this one is Fe2. Both are the octahedral sites. What is the meaning for this? It means that it is not specifically the Fe3 is only undergoing to have the octahedral complexation or octahedral geometry with the oxide, but Fe2 is also creating the octahedral. So therefore, we cannot specify that this is only the iron cation in oxidation state 3 or 2, but both are creating the octahedral geometry. Whereas this one is tetrahedral, right? And this is only Fe3. So it means that the tetrahedral position of the iron is created by Fe3, but the octahedral position are created by both Fe2 as well as Fe3. So therefore, the entire unit cell is very complex structure. So therefore, instead of putting it in just one, so they exist in the 8 subshells, and eventually when you count all the ions in the form of the atoms, and you can settle with that of the molecular formula of our iron oxide. Now, uh, earlier when we were talking about the crystalline solid state, where we were talking about we were calculating that how much surface area of a particular atom is included in the unit cell. At that time, there was no position at this point. So what is this? Because we talk about the position on the vertices. This is the corner, and we call them the vertices. We also talk about the positions on the faces. So the that is its 1/8 position is included in the unit cell. The atom which is on the face, its half of the position is included in the unit cell.
Atom is exactly on the edge. How much more
Amount of the surface area is included in the unit cell. How much? So he says 1/4. Do you agree? This is a cube
here, and it means that it is shared by. Yeah, basically he is correct. But I am just figuring out that is there any way we can put yeah. So there is one cube, the one this is shown over here.
right? I can place another cube over here, and then the same layer above it. Correct? Put any more cube which can be shared by this. Am I correct? So therefore it is 1/4 only. So therefore you have to keep in your mind, you're going to get a question anywhere in the exam where these are the main three positions: vertex, face, and the edge. So therefore you should keep in your mind that how much surface area can be included when the atom is placed at the vertex or at the face or at the edge. Otherwise, the atom, this one is included inside, this one is included inside, there is no issue with that. Okay, so this of the unit cell, the story is slightly complicated. I just wanted to give the detailed picture so that whatsoever we have defined in the fundamental sense of the solid state geometry, so that we should conclude the formula of the iron oxide particle by whatsoever we have understood in the previous lecture. Going ahead now. Now we are dealing with the magnetic property. This was the crystal structure. Okay. Now we are going ahead with the magnetic properties. Though uh, uh, Dr. Rajiv has already explained everything in detail regarding the magnetic properties, but I am going to give you the sense that why iron oxide is susceptible to external magnet in terms of the dipole moment. This is the top view over here.
Here,
This color belongs to iron 2 plus oxidation state. This one iron 3 oxidation state. This one is also iron 3 oxidation state, octahedral, and tetrahedral, and this is oxide. See above. This color is Fe2 plus, and this yellow color is Fe3 plus. You see their dipole moment are exactly opposite to one another. So it means that it is the same way. If we are going to have the magnet with the north and the south pole, one magnet over here, there is another magnet over there, right? If I'm having the north and the south, and again south and the north, then the same pole are going to repel the magnet. So I cannot have the magnetic susceptibility, right? The magnetic susceptibility means that the dipoles, magnetic dipole, must align to the external magnetic field. So hence in this way, the substance is going to be susceptible to the external magnet and will respond to the external magnetic field. So it means that uh, the magnetic moment, magnetic dipole moment, that is contributed by these two positions, octahedral, octahedral this one, Fe2, and the tetrahedral Fe3 yellow, they are cancelled with each other. And what is remained? You see the green one. that remained. So it means that the magnetic susceptibility for the iron oxide is essentially contributed by iron in oxidation 3, which is in the tetrahedral configuration. So it is shown over here. So there are how many? Octahedral, there are 8 lattice sites for the iron 3 plus. Tetrahedral, so there are 8. You see that with the opposite one, the effect of this one is cancelled by opposite magnetic moment of the other one. But this one survives.
So it means that here is a complete cancellation. So whatsoever the magnetic field or magnetic susceptibility,
which you see in terms of the superparamagnetism, Dr. Rajiv explained. So that is being originated by the iron in the oxidation state 2 plus. Okay, so this is simply the basic structure. We are not going ahead. This much information is sufficient in order to understand that what is the origin of the magnetic susceptibility in iron oxide Fe3O plus magnetic nanoparticles.
this is a kind of instrument which helps us to determine that if the nanoparticles are susceptible to magnetic field or not. Simply what we do, it is the same thing which Dr. Rajiv explained. So here we have the plot of the flux density. It's the field and flux density generated inside and of the magnetic field, and we are going to vary with that of the magnetic field strength. You see that initially when
we are going to simply apply the field strength at a minimum magnitude, the dipole magnetic randomly. But when we keep on increasing,
aligning to that the magnetic field, and eventually, so by increasing further magnetic field strength,
their alignment is simply positions, and no more change is happening. That is the supersaturation. This particular
curve, which is known as hysteresis curve. So this hysteresis curve is
typical kind of a curve for the iron oxide nanoparticles whose size is very, very low. A very small size, they show an extraordinary effect of super paramagnetism, the one Dr. Rajiv explained, and so therefore I'm not going to repeat that, but I have no more information than Dr. Rajiv, whatsoever Dr. Rajiv explained, right? So this is, somebody asked you that how can we determine a particular sample is susceptible to the magnetic field? No doubt, qualitatively, you can simply place the external magnet and see if the nanoparticles are attracted to that. That is the best way of qualitative information which you are going to get. Quantitatively, you have to perform this experiment to calculate the parameters. So, these parameters, in fact, explain the complete information about the magnetic properties. Okay, so important
which I want to specify, iron oxide nanoparticle, that is a rust,
exist in two forms,
magnetite and hematite. The magnetite is the one which we talk about over here, Fe3O4. In fact, it is the combination of F3O, iron oxide, and Fe2O3. So these two kinds of
iron oxide, when they combine, so the combined composition of these two kinds of the oxides, they create Fe3O4. So the best way, there are other instrumental studies which can help us to determine if the iron is in oxidation state 2. Here you could see that.
And here the
Iron is in oxidation state 3. Am I correct? Do you agree with this? Iron, here it is oxidation state 3. Here it is oxidation state 2. So that is the reason where I explained here there are two kinds of oxidation state of the iron positions, Fe3 plus and Fe2 plus. The reason is because the composition of iron oxide that is composed by the combination of iron 2 plus oxidation state and iron 3 plus oxidation state. And such a composition is known as magnetite, and where you could see only the oxidation state of iron plus 3, that is hematite. What is the difference? Difference is oxidation state 2 and oxidation state 3. Here only oxidation state 3. Magnetite iron content higher than hematite. So here when you have uh, the material composition, you may have magnetic nanoparticle or not, or even if the rust, you're talking about the rust. So the iron content is higher than that of hematite. That is obviously, you know, from. So it is Fe3 rather than Fe2. Then magnetite, color of the magnetite is black in color. And you have already synthesized because your today's experiment, when you performed the experiment, you added the ammonium hydroxide and you instantaneously saw the color, black color of the suspension. That is because of that the synthesis nanoparticle which you produce during the course of the reaction, those Fe3O4, and they were magnetite, and hence they had the black color. Right, that was the reason you got the black color. But hematite varies with color. Usually that is bright brown color. If you get the brown color suspension, then the composition predominantly is Fe2O3, that is hematite. But if you get the black suspension of the magnetic nanoparticle, so then it is the magnetite. Hematite rust component, magnetite not. Magnetite strong magnet, hematite heating induced magnetism. So it is a strong magnet. So as you've already seen that I think you have already observed from after the reaction, if you are going to place the magnet close to the reaction vessel, all the particles, magnetic particles were rushing towards the magnet. So it means that they were magnet. And the crystal structure rhomboidodecahedral. So first you need to know that what is decahedral, then dodecahedral, and then hedral. So that is the crystal structure. So I mean to say that this you could take it as a homework and you should see and try to see that what is the crystal structure for, or the shape of the crystal structure that is because of the rhombo-dodecahedral. Magnetized octahedral crystal structure. So I just wanted to introduce this slide because the common name particle which you have produced, that is the magnetite. So that was the reason. But sometime when you put the word magnetite somewhere on the internet, and you may get confused why you are getting, there is another word appearing that of the magnetite. So therefore, I thought that we should have a slide where we could few contrasting difference between the. So though I have mentioned that most of the nanoparticle which we use, the active or the water soluble. So usually the shape and size of those nanoparticles is something like this, close to 25, 30 or 40 nanometers. Sometimes cubic structures, hexagonal shapes, or those kind of, you may say the bar-shaped structure. And so mostly the synthesis produces such kind of geometries or the shapes. But apart from this, if you choose a different pattern and try to see that if there is structure alteration, shape or alteration of the nanoparticle. Yes, then it happens. We have observed that when we do not add any additive, the reaction you have performed today, I'm not sure if you use any surface active molecule or not. Have you used
Specific
surface active?
molecule today for the salt when you perform the reaction? What was that? Or which one? Okay, yeah. yes. Sorry about that. Actually, I forgot. That was Gemini surfactant. Yes, correctly. So
The main reason for that was actually we wanted to produce surface active. These are the water soluble, in fact. So because they are not Gemini surfactant, you see, Gemini means identical to, right? So, but here form, right? So therefore, it is not the Gemini surfactant.
when you do not add any surfactant,
And still you get the shape and size of the nanoparticle, something like this. Always try to read the scale bar, it's 20 nanometer. This one is 50 nanometer when you are using this sugar derivated surfactant, right? So the shape is not much different. But you will be surprised to see when you are going to see there is the concentration of sodium dodicyl sulfate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Correct. C12 means dodicyl. When you are choosing this kind of a surfactant, it is not the principal amount which you are going to get, but this is also a small amount of the rods produced. You see, they are all
rods of
iron oxide, right? Though we have not used them because for the time being we are using only the particles like this, small particles. And suppose if you ask me that, can't we use the rods for the purification of water? I would say that the greater surface area is provided by the
or facilitated particles like this, small particles in comparison to very big long rods. So you see the 200 nanometer scale, right here 20 nanometer, 50 nanometer. This much length is to 200 nanometer. If you want to see the length of this nanorod, we call it nanorod because still it is in the nanometer region. So it should be around 200, 400,
close to 500 nanometer. 500 nanometer is the length of the nanorod. So for the surface active nanoparticle, though we have not seen the production of nanorods, but for STS also at certain concentration produces the surface active magnetic nanoparticle. STS, but at those concentrations we have now never seen the synthesis of rods. But if you alter the concentration at some point, you will see the rods. Likewise, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. What is the name of this one? If the hydrocarbon chain is C16, is it dicyl, dodecyl, tetradecyl, hexadecyl, or octadecyl? So this one is hexadecyl. So likewise, the sodium dodecyl surfactant, this trimethyl, a very common cationic surfactant you use most of the time. So this also produces, you have the rods over here.
Practically they are similar to the one they are being produced over here. But
According to experience, very few people in fact are working in this field. It's just a new field. We have initiated this. Probably we are the first group to start this field for the surface active. I'm not showing the iron oxide synthesis. I'm talking about the surface active iron oxide nano. So our publications are the first one, right? And we have created the nanomaterials which are surface active. Otherwise, all nanomaterial publications you would see, they are published and they're all water soluble or suspended in the aqueous phase with stable suspensions. I'll take few minutes to explain
the growth. So how the growth is happening.
So if you have a something hexagonal shape of the seeding particle, we call it seeding because those nucleating centers which are involved in the further growth during the course of the crystal structure, so their shapes vary. So here I can simply, if you suppose ask me how the rod or the bar can be produced, hexagonal nucleating center. This is the lateral face, and so this is base and base. You can take it over here, right? But if the growth is impeded, blocked on the one side, so here it is blocked on the base, and it's allowed on this lateral faces. When the lateral faces are going to grow like this, there is another lateral face on the opposite side that grows like this. You can convert hexagonal shape into the cubic shape, and the cubic shape then extends and converts into a bar. Bar is basically the length is more, whereas width and the height may be the same. Right? So you could see that if we allow the nucleation to happen only over here, right, then this shape can be converted into this shape, provided you have blocked the other faces. The other faces of the hexagonal shape should be blocked, and then, so, and suppose if you ask me that how can we do, as I mentioned previously, that it's not that easy to explain. It is the experience, and slowly when you perform the experiment and you see that by using this surfactant or that surface active, you can alter the shape from this to the other one. If you are having something the shape like this, and this can be converted into a cube like this, and from cube the platonic solids. So you see there are several vortices over here. So such kind of shapes are known as platonic solids. So otherwise, you can convert into nanorod if you are specifically blocking the crystal or the sides of the nucleating center. This one is what is the meaning of the nucleating center? I mean to say that nucleating center in the crystal growth is that entirety which is involved in the crystal growth, and that is not the final structure or the final shape of the nanoparticle. That is still continuing to grow during the course of the reaction. That is the nucleating center. Now we are going ahead with how we can use them. So here I'm going to show you there are two kinds of nanoparticle. The earlier I showed you the application of the surface active. Here I'll be showing the application of the surface active magnetic nanoparticle in protein conjugated, extraction of protein conjugated nanoparticles. Suppose in biomedical field, you are using the gold nanoparticle in some kind of biological application. Wherever you are going to use in the biological applications, amino acids, protein, biomolecules are always there. So then the gold nanoparticles are going to complex wherever the nanoparticles are going to use. Now suppose you have used them for certain biological application, maybe in the wound healing, somewhere over there, right? Now you want to extract them. You cannot leave them in the human biological system because they are the transition metal particle. They are not going to dissolve, right? And you have a suspension of some biological fluid where the gold nanoparticles are present. You want to extract them. So then the best way is you take the surface active magnetic nanoparticle. So here is the protein conjugated nanoparticle suspension. You see the purple color? The purple color means the nanoparticles are aggregated to that of the protein, right? And you want to, rather than using the centrifugation or the filtration process, you want the easiest way, you can simply separate out the protein coated nanoparticle. You may use that in order to characterize a certain protein which has adsorbed on the surface of the nanoparticle. So by placing the surface active magnetic nanoparticle, you will see that all the protein coated nanoparticles are attracted to a surface active magnetic nanoparticle. In the case of cleaning the contaminated water, I told you that it is the electrostatic interactions which which play their part. But you have the, if you have the protein coated nanoparticle and they are being extracted by the surface active magnetic nanoparticle, then what kind interactions you are expecting. So here I am going to show only one surface active nanoparticle, and this surface active nanoparticle is coated with Gemini surfactant. The And on the other hand, I have gold nanoparticle. The gold nanoparticle I have, so that is coated with the protein. So I can say that this is gold. This one is with the protein. Now, according to this experiment, it clearly shows that extracted from the aqueous bulk by the surface active. So this is surface active magnetic nanoparticle. This one is protein coated gold nanoparticle. What kind of forces you are expecting? So protein is amphiphilic molecule. You can say it's a polymer, biopolymer. It has hydrophobic domains, hydrophilic domains. Likewise, the gem over here is also amphiphilic molecules with clear the polar head groups and the non-polar hydrophobic tails. So therefore, what happens when the protein coated nanoparticle is dissolved in water? It is not in the native structure of the protein. So the protein, when adsorbed on the solid surface, most of the time it gets unfolded. So hence its non-polar as well as the polar domains, they are exposed to the aqueous phase. So hence, what kind of interactions? The hydrophilic,
and the hydrophobic.
So hydrophobic. Hydrophilic, suppose if I'm saying that this is Gemini surfactant, positively charged, it is going to interact with the predominantly hydrophilic domain. And on the other hand, if I have to show this kind of arrangement, then this will be the hydrophobic domain. So this is hydrophilic domain of protein,
And
this is hydrophobic. Do you agree that such interaction here and here? And why? The hydrophobic domain is predominantly nonpolar. The hydrocarbon chains are predominantly nonpolar. So hence this kind of non-polar interactions are going to predominate over here. Hydrophilic domains is predominantly polar, and the head group is polar, obviously. So polar interaction, and that is the reason that is extracted. So both kind of interactions, they are in action when we have to extract the protein coated nanoparticle from any biosuspension. Now, in general words, so there are plenty of biosuspensions when you go to hospital. So the samples are being taken by the analyst and performing the analysis. They are throwing that somewhere over there. And or sometime you are dealing with the unknown biological matter or certain kind of the protein extraction from the plants or anywhere. So that protein extraction, if you're going to put the gold nanoparticle, the protein is going to absorb. And then if you place the magnetic nanoparticle, the gold nanoparticle can be extracted. Place the magnet, remove the sample, and purify it. And then you need to estimate how much amount of the protein is extracted. So simply by using the protein estimation, it's a Bradford method, very common. Everybody uses this method in when you deal with the biological class, right? So that can help you to quantify the amount of the protein which you have extracted. So I'm going to say of opportunities like this, where you can apply this this application of the extraction of biological matter. Next one. So here is it is not only the surface active molecules, but if you want to extract the gold coated protein coated gold nanoparticle, you can also use the water soluble magnetic nanoparticle. So here, water soluble. So the red color particles, they are exactly adsorbed at the interface, so hence they are surface active. Here red color particles embedded in the aqueous phase, they are water soluble. I have already explained the hydrophobic domain. They are in action. If we are using this particular picture, the diagram is from the experiment that was predominantly hydrophobic. So that's why I have only shown you the hydrophobic domains. But I have here mentioned that it could work hydrophilic domains as well. So the protein is predominantly occupying the hydrophilic domains, so still the extraction is happening. And if you are choosing the water soluble with the protein coated gold nanoparticle, now when they are in the bulk, then because you see here it is particularly shown the hydrophilic domains. So when in the water aqueous bulk phase, in the aqueous bulk phase, the protein coated nanoparticle are predominantly hydrophilic domains. As I showed you, if this is dissolved in water, so then the protein which is on the surface is predominantly hydrophilic proteins, and that's why this hydrophilic proteins is going to interact with the polar part. Here they are showing the non-polar tails interacting with the hydrophobic domains, but here the head groups are interacted with the hydrophilic domain. So in this way, I meant to say that the close-up picture for the magnetic nanoparticles, both kind of magnetic nanoparticles, either surface active or water soluble in action when extracting the protein-coated nanoparticles from the biological suspension. So we have another one. We perform experiment. So here we took specifically the Gemini surfactant. Suppose if we do not take the Gemini surfactant, and if you want to perform still, because Gemini surfactants are usually not available commercially, you have to synthesize them. If someone wants that, somebody says that, yes, I want to extract the protein from the biological suspension, but the problem is I do not have the Gemini surfactant, and I do not have the expertise to synthesize the Gemini. What is the easiest way to perform this kind of extraction? So then you will be saying that is not a problem. So you can have the magnetic nanoparticles coated with a conventional surfactant. So here you can see this is the conventional surfactant. It is zwitterionic surfactant, positive charge
and the negative charge. You see in
the head group.
So wherever in the head group you see the positive and the negative charge in
the polar part. So that is the zwitterionic. If only the positive charge, it is cationic. If only the negative charge, it is anionic. If there is no net charge, it is non-ionic. So sometimes what we have seen that works favorably with the Zwitterionic surfactant rather
than with the cationic
than
surfactant.
surfactant.
You
You
see
see
over
over
here,
here,
it
it
is
is
negatively
negatively
charged. We have actually created a negatively charged protein by dissolving the water insoluble protein in
in SDS solution, that is an ionic surfactant. And we have now the nanoparticle which is possessing the negative zeta potential. And then we also created the nanoparticle coated with the protein with zeta potential positive. Zeta potential is basically uh, uh, the parameter which helps you to determine the overall charge on the nanoparticle. So here it is the negative charge, and here it is the positive charge. What we have observed that the attraction for a
nanoparticle when it is possessing the positive zeta potential is much more stronger in comparison to the negative zeta potential. Now, what is the problem? The head group is over here that is interacting, same head group is over that is interacting. But now, you might have
heard about or read in the organic chemistry the steric hindrances. And you have already learned the organic mechanism where you have seen that if there are steric hindrances during the mechanism, so then that step is not favorably obeyed during the course of the reaction. So the same thing is happening over here. This functional group is sterically shielded by this functional group, which is negatively charged, this is positively charged. So in order to extract this functional group must be freely available for this negatively charged nanoparticle coated with the protein. Only this will be extracted. If this is sterically shielded by, screened by some other functional group, then this kind of interaction is not going to happen at a required amount of the attractive interaction, and the extraction is not going to happen. Very less amount of extraction or extraction may not happen in that case at all when the interactions are not stronger. But when the interactions are stronger over here, there is no steric hindrances. You see, it is the terminal group. There is no steric hindrance. Then in that case, the interactions are so strong that the extraction is happening instantaneously. So therefore, there are several factors. I intentionally this slide to just demonstrate that it's not simply the electrostatic interactions in action during the extraction. It is the other factors which drive the extraction, though in both cases you have the as well as over here. But why this one is fruitful in comparison to this? The reason is there are little steric hindrances over here, and there are steric hindrances. There is a little steric hindrances. Extraction is favorably carried out. In conclusion, functional magnetic nanoparticles, such kind of particles are known as functional magnetic nanoparticle, where you could change the adsorbed molecule functional group. So use different kind of surfactant for different applications. They are the functional magnetic nanoparticle. Functional magnetic nanoparticle interact selectively with biomolecules, right? So there you may think that the electrostatic interaction must work, but it's not the case. It is the other factors which are going to decide if the extraction is happening or not. That is the meaning of selectivity. Materials can be performed by carefully manipulated with the functional
magnetic nanoparticles of biomolecules. So I mean to say that whenever
whenever
you
you
have
have
to,
to, biomolecules are very big. Most of the time, they are the polymeric molecules. So therefore, wherever you have to perform the extraction of the biomolecules for bioapplicability, you have to be very careful that the selectivity is going to induce its effectiveness during the extraction. this is all about regarding this lecture. Hope you enjoyed it. It was slightly complicated, and thank you so much for your attention. Any question, please? Absolutely, wonderful question. Yes. Any free, first thing you have to keep, any free surface, no matter of which material it is, has the ability for the adsorption of the molecules, right? So, because the reason is that the free surface is in fact the interface where you have the interfacial energy is very high, right? The interfacial energy of the top layer of the molecule is very high because they are not simultaneously attracted in different directions. They are only attracted kind of molecules are present on one side, whereas the upper side is completely exposed to different kinds of molecule which have no preference for the molecular type of interaction. So therefore, any surface is very prone for the adsorption of any kind of molecule, particularly the transition metal nanoparticles like the gold. So as I told you, they have the mobile electron cloud. So the surface is highly potent to interact with any kind of amphiphilic molecules. The proteins are amphiphilic molecules, and you will see there are plenty of applications, plenty of the American Chemical Society journals. You will see there are plenty of publications where how the protein adsorb or prefers to absorb on the metallic surfaces. So whenever the protein prefers, the first thing you have to keep in your mind, no matter which protein you are going to talk about, but the protein has to be in some sort of suspension. If you are going to expose this to the metallic surface, whether the nanometallic or any other metallic surface, right, the protein is instantaneously going to be absorbed because protein itself is a very big polymeric amphiphilic molecule. There are hydrophobic as well as hydrophilic domains. You have only two kinds of attractive interactions, whether polar interaction, non-polar interaction. You will not see where the polar function groups are going to be interacted with the non-polar. So the protein molecules have both possibilities, hence they can easily be absorbed on the transition metal surfaces, and whenever the protein is going to absorb, it is preferably try to defold. And so therefore, it's not a new concept, it's a well-studied concept. The protein molecules, they have high affinity to be absorbed on the metallic surfaces. Any other question? Okay, then see you tomorrow. So free lecture tomorrow, very entertaining, very interesting, though according to me, hopefully you will also enjoy. Thank you, see you.